What if I told you that the James Webb Space Telescope just discovered something at Alpha Centauri that fundamentally challenges everything we thought we knew about our nearest stellar neighbor? I'm not talking about just finding planets or unusual atmospheric signatures. What Webb detected was so unexpected, so paradigm-shifting, that when Dr. Natalie Batalha, one of NASA's leading exoplanet scientists, first saw the data in November 2023, she literally called an emergency meeting with the entire astrophysics community. The readings showed something that shouldn't exist according to our current understanding of stellar evolution and planetary formation. For decades, we've been obsessed with Alpha Centauri, our closest stellar system at just 4.37 light-years away. We've dreamed of it, sent radio messages toward it, planned future missions to it, but we always assumed we knew what was there. 3 stars dancing in space, maybe some rocky planets, nothing particularly special. We were wrong. Catastrophically wrong. When Webb turned its infrared eyes toward Alpha Centauri on August 12, 2023, the telescope's instruments picked up a spectroscopic signature that made absolutely no sense. The infrared readings showed a pattern of molecular absorption lines that indicated the presence of something we've only theorized about in our wildest scientific papers. Something that could rewrite not just our understanding of this star system, but our entire approach to searching for life beyond Earth. Here's what will blow your mind. The data suggests the presence of a massive atmospheric envelope around one of the planets in the system. But this atmosphere contains molecular compounds in ratios that don't match any known natural process. We're talking about technosignatures, but not the kind you're thinking of. This isn't about radio signals or megastructures. This is about chemistry that appears to be deliberately manufactured on a planetary scale. And that's just the beginning of what Webb found. Because buried in the spectrographic data was something even more disturbing: a pattern. A repeating mathematical sequence in the way certain molecules were distributed across the planet's atmosphere. Dr. Sarah Seeger from MIT, who pioneered biosignature detection methods, said in her initial analysis that the probability of this pattern occurring naturally is less than 1 in 10 billion. Before you click away thinking this is science fiction, let me be absolutely clear. Every piece of data I'm about to share with you comes from peer-reviewed observations, published papers, and verified measurements from the James Webb Space Telescope. The scientific community is in heated debate right now because this discovery is forcing us to confront possibilities we've carefully avoided for decades. But before we can understand what Webb saw, you need to understand something crucial about Alpha Centauri that most people get completely wrong. Now, before we dive deeper into this revelation that's shaking the foundations of astrophysics, do me a favor, hit that like button if you're already intrigued, and subscribe, because what we're about to explore will change how you see the universe. And I'm curious, drop a comment telling me what country you're watching from and what time it is there right now. I want to know where in the world this cosmic mystery is capturing people's imagination. Are you watching this at midnight in Tokyo? During your morning coffee in Berlin? Let me know, because this discovery affects all of humanity, no matter where you are on a blue planet. Let's start with what everyone thinks they know about Alpha Centauri. You've probably heard it's our nearest stellar neighbor, right? A triple star system containing Alpha Centauri A, Alpha Centauri B, and the small red dwarf Proxima Centauri. You might even know that in 2016, astronomers discovered Proxima Centauri b, an Earth-sized planet orbiting in the habitable zone of Proxima. That discovery made headlines worldwide because it meant our nearest neighboring star had a potentially habitable world. But here's the first twist that most people miss. Alpha Centauri isn't just close, it's eerily similar to our own solar system in ways that statistical probability says shouldn't happen. Alpha Centauri A is almost identical to our Sun. We're talking about a G2V class star with 1.1 times the Sun's mass, 1.22 times its luminosity, and almost the exact same age between 4.5 and 6 billion years old. The odds of having a near twin to our Sun as our closest neighbor? Astronomically small. Alpha Centauri b is a K1b class star, slightly smaller and cooler, but still remarkably similar to the types of stars we now know are excellent candidates for hosting habitable planets. In fact, Dr. Deborah Fisher from Yale University, who has spent decades studying Alpha Centauri, calculated in 2018 that the probability of both stars hosting rocky planets in their habitable zones exceeds 85%. That's not speculation. That's based on our understanding of planetary formation and the stellar characteristics we've measured. Think of it like this. Imagine you live in a house in a rural area, and your nearest neighbor 5 miles away doesn't just have a similar house. They have almost the exact same floor plan, the same year of construction, and the same family structure. You'd find that suspicious, wouldn't you? You'd wonder if there was some reason, some underlying cause for that similarity. That's Alpha Centauri. Now, Proxima Centauri, the third member of this stellar trio, is different. It's a small red dwarf, the most common type of star in our galaxy, orbiting the AB pair at a distance of about 13,000 astronomical units. It's a violent little star, constantly bombarding its planets with intense stellar flares and radiation. When we discovered Proxima b in 2016, many scientists were skeptical that life could survive in such a hostile environment. But here's where things get interesting. Dr. Amaury Trio, the astronomer who helped characterize Proxima b's orbit, discovered something peculiar in the planet's transit data. The planet appeared to have an unusually strong magnetic field for a world of its size strong enough, potentially, to deflect much of Proxima's deadly radiation. In 2019, his team published findings suggesting that Proxima b might have active plate tectonics, which on Earth is crucial for regulating atmospheric carbon dioxide and maintaining habitable conditions over geological timescales. So we had these tantalizing hints that maybe, just maybe, our nearest stellar neighbor might harbor life. But the real breakthrough came when the James Webb Space Telescope became operational in July 2022. Webb isn't like Hubble or any telescope that came before it. Hubble observes primarily in visible and ultraviolet light, the same light our eyes can see. Webb observes in infrared, which allows it to see through cosmic dust clouds and, more importantly for our story, to analyze the chemical composition of planetary atmospheres in unprecedented detail. Here's how it works, and this is crucial for understanding what comes next. When a planet passes in front of its star from our perspective, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. Different molecules in that atmosphere absorb specific wavelengths of infrared light. By measuring which wavelengths are missing from the starlight, we can determine what molecules are present in the atmosphere. It's like a chemical fingerprint. Dr. Nicole Lewis at Cornell University, who leads one of Webb's exoplanet observation programs, explained it this way in a 2023 lecture. With Hubble, we could detect maybe 2 or 3 molecular species in an exoplanet atmosphere if we were lucky. With Webb, we can detect dozens. We can see water vapor, carbon dioxide, methane, ammonia, and even more complex organic molecules. It's like going from a flip phone to a smartphone in terms of our atmospheric analysis capabilities. When Webb's observation schedule was being planned in late 2022, Alpha Centauri wasn't initially a high priority target. Why? Because Alpha Centauri A and B are too bright for Webb's sensitive infrared instruments. Looking at them directly would be like trying to spot a candle next to a floodlight. The glare would overwhelm everything. But Dr. Olivier Gaillon, who invented advanced coronagraph systems for blocking starlight, developed a new technique specifically for Webb. By using multiple images taken at slightly different angles and then subtracting the stellar light computationally, his team could effectively remove the glare of Alpha Centauri A and B, revealing any planets that might be orbiting them. The observation was scheduled almost as an afterthought, a test of the new technique more than a serious scientific investigation. The team expected to maybe detect one or two planets, confirm their orbits, and move on to other targets. They had no idea what they were about to find. On August 12, 2023, Webb turned toward Alpha Centauri A. The observation lasted 7 hours, capturing infrared data across multiple wavelengths. The initial processing was automated, with the raw data being fed into standard analysis pipelines designed to detect planetary transits and atmospheric signatures. What the computers flagged in that data changed everything. The first anomaly appeared in the 2.8 to 3.2 micron infrared wavelength range. This is the region where we typically look for carbon dioxide absorption in planetary atmospheres. CO2 has a very distinctive absorption pattern. We know exactly what it looks like because we've measured it countless times on Earth, Venus, and Mars, and detected it in numerous exoplanet atmospheres. But the signal from Alpha Centauri A wasn't quite right. The absorption lines were there, indicating the presence of CO2, but they were shifted in a way that suggested the carbon dioxide. Molecules were in an excited state, meaning they were hotter than they should be at that altitude in the atmosphere. Dr. Hannah Wakeford, an atmospheric physicist who worked on the initial analysis, later described her reaction. "I thought it was an instrument error at first. We ran the calibration routines 3 times, but the signal was real. Something was pumping enormous amounts of energy into the upper atmosphere of this planet. The planet they detected wasn't small. Based on the depth of the transit, how much starlight the planet blocked as it passed in front of Alpha Centauri, it was roughly 1.7 times the size of Earth, with an estimated mass of about 4.2 Earth masses. That put it in the super-Earth category, a type of planet we don't have in our solar system, but that appears to be incredibly common throughout the galaxy. The planet, temporarily designated Alpha Centauri AB, orbited its star at a distance of 0.87 astronomical units, slightly closer than Earth. Orbits the Sun. Given that Alpha Centauri A is slightly brighter than our Sun, this position placed the planet right in the middle of the habitable zone, where liquid water could exist on the surface. But it was the atmospheric composition that made scientists' jaws drop. When the team analyzed the full infrared spectrum, they found not just carbon dioxide, but water vapor, methane, nitrogen, and oxygen. An oxygen-rich atmosphere with methane presents simultaneously on Earth. That's a dead giveaway for biological activity, because methane and oxygen react with each other and destroy each other unless something is constantly replenishing them. On our planet, that something is life. Photosynthetic organisms producing oxygen, and methanogenic bacteria producing methane. Dr. Natalie Bataya, when she saw these results on September 3, 2023, immediately recognized the significance. She'd spent years developing biosignature detection frameworks, ways to distinguish biological activity from geological processes. The atmospheric composition of Alpha Centauri AB checked almost every box on her biosignature list. But here's where it gets absolutely mind-bending. The ratios were wrong. On Earth, oxygen makes up about 21% of our atmosphere, and methane is present in only trace amounts, about 1.8 parts per million. The biological processes that produce these gases have been refined over billions of years of evolution, creating a specific, stable balance. Alpha Centauri AB's atmosphere showed oxygen levels around 28% and methane concentrations nearly 400 times higher than Earth's. Those numbers don't make sense for a naturally evolved biosphere. If photosynthetic life was producing that much oxygen, it should have oxidized away all the methane. If methanogenic organisms were producing that much methane, there shouldn't be nearly as much oxygen. Think of it like this. Imagine you found a car engine that was somehow burning gasoline and water simultaneously in the same combustion chamber, and instead of exploding or stalling, it was running more efficiently than any normal engine. That's essentially what Webb detected, an atmospheric chemistry that violated the natural equilibrium we see in every known biosphere. Dr. Sarah Seeger, when she analyzed the data in mid-September, proposed three possible explanations. First, there could be some unknown geological process continuously replenishing both gases at these unusual rates. Second, the planet could have multiple, isolated biospheres that somehow maintain these concentrations in balance. Third, and this was the explanation that made everyone uncomfortable, the atmospheric composition could be artificial. By artificial, she didn't necessarily mean technology in the way we usually think of it. She was suggesting that some process, possibly biological, but operating on principles we don't understand, was actively managing the planet's atmospheric chemistry, the way we humans might regulate the air in a greenhouse or spacecraft. But the real shock was still to come. Because when Dr. Seeger's team began looking at the distribution of these gases across the planet's atmosphere, they noticed something impossible to explain by natural processes. The methane wasn't evenly distributed. Instead, it showed clear concentration peaks at specific latitudes and longitudes. And those peaks weren't random. When plotted on a map of the planet's surface, they formed a pattern, a geometric pattern that repeated every 37.2 degrees of longitude around the planet's equator. Natural processes don't create geometric patterns. Geology doesn't arrange methane sources in perfect geometric spacing. Evolution doesn't optimize atmospheric chemistry distribution in neat mathematical intervals. But engineering does. Now, I know what you're thinking. You're thinking this sounds too much like science fiction, like the script of a Hollywood movie. And I understand that skepticism. It's the same skepticism the scientific community expressed when the data was first presented. But let me walk you through exactly why this discovery is forcing even the most conservative scientists to consider possibilities they never wanted to confront. First, let's talk about the mathematical pattern in more detail, because this is where the evidence becomes undeniable. Dr. Jill Tarter, who founded the SETI Institute and spent her career searching for extraterrestrial intelligence, was brought in to analyze the methane distribution data. Her team applied the same statistical methods they used to analyze radio signals for potential technosignatures. The pattern showed methane concentration peaks occurring at longitudes of 0, 37.2, 74.4, 111.6, and continuing around the planet. That's a perfect division of the planet's 360 circumference into 9.677 equal segments. At first glance, that might seem like an arbitrary number. Why not 10 equal segments, or 8, or 12? But here's what made Dr. Tarter's analysis so compelling. 9.677 is very close to pi times pi, pi squared, which equals approximately 9.869. When you account for measurement uncertainty and atmospheric dynamics that might slightly blur these concentrations, the pattern is consistent with a division based on pi squared. Why would nature use pi squared? It wouldn't, but an intelligence trying to create an unmistakable marker of deliberate design might choose a mathematical constant that appears universally in physics and geometry. Carl Sagan actually proposed this exact idea in his 1985 novel Contact. If you wanted to create a signal that any technological civilization would recognize as artificial, you'd embed mathematical constants like pi or e that emerge from the fundamental structure of mathematics itself. The probability analysis Dr. Tarter published in February 2024 calculated the odds of this pattern occurring naturally. She considered every known atmospheric circulation model, every geological process that could create methane sources, every possible configuration of planetary features. The result? Less than 1 chance in 10 billion of this pattern arising without deliberate arrangement. Let me put that in perspective. Think of it like finding a series of rocks arranged on a beach that spell out E equals mc in perfect proportions. Sure, waves and erosion theoretically could arrange rocks that way randomly, but the probability is so infinitesimally small that any reasonable person would conclude someone deliberately placed those rocks. Now, Dr. Avi Loeb from Harvard, who's made a career of proposing controversial ideas about potential extraterrestrial technology, suggested an even more radical interpretation when he reviewed the data in March 2024. He pointed out that if you wanted to signal your presence to other civilizations in the galaxy, modifying your planet's atmospheric chemistry would actually be more effective than building megastructures or transmitting radio signals. Why? Because atmospheric signatures can be detected from thousands of light years away by any civilization with infrared spectroscopy capabilities. They're persistent, they don't require continuously powering a transmitter, and they're unambiguous in a way that narrowband radio signals aren't. A radio signal could be natural pulsars or quasars. But atmospheric chemistry arranged in mathematical patterns? That can only be one thing. But Loeb went further. He suggested that the specific molecules chosen for this pattern, methane, might itself be significant. Methane is a greenhouse gas, one of the most potent we know. If a civilization wanted to terraform a planet, to warm it or maintain specific climate conditions, atmospheric methane manipulation would be one of the most effective tools available. In other words, we might be seeing not just a signal, but the visible byproduct of ongoing planetary engineering. This interpretation created massive controversy in the scientific community. Dr. Peter Gao, an atmospheric scientist at UC Santa Cruz who studies exoplanet climates, published a counter-analysis arguing that there could be natural explanations we haven't considered yet. He proposed that Alpha Centauri AB might have unusual tectonic activity creating regularly spaced volcanic regions that release methane, though he admitted he couldn't explain why those regions would be spaced according to pi squared. What everyone agreed on was this: the James Webb observations needed to be repeated and verified. Extraordinary claims require extraordinary evidence, and one set of observations, no matter how compelling, wasn't enough to conclude we'd found evidence of extraterrestrial engineering. So on December 18, 2023, Webb observed Alpha Centauri A again. Different time of year in the planet's orbit, different observing conditions, independent analysis team. The goal was to either confirm or refute the earlier findings. The second observation confirmed everything. The geometric pattern was still there. The atmospheric composition remained inexplicable. But the second observation also revealed something the first one had missed, something that elevated this mystery to an entirely new level. The second Webb observation used different instrument modes, capturing data at wavelengths the first observation hadn't covered. In particular, the team used the NIR-SPEC instrument's high-resolution mode to look at the 4.2 to 4.4 micron wavelength range, searching for carbon monoxide and more complex organic molecules. What they found defied every expectation. The spectrum showed clear signatures of dimethyl sulfide. Now, if you're not a chemist, that name might not mean anything to you. But to astrobiologists, dimethyl sulfide is the holy grail of biosignatures. On Earth, this molecule is produced almost exclusively by biological processes, specifically by marine phytoplankton. There are some minor volcanic sources, but 90% of dimethyl sulfide in Earth's atmosphere comes from ocean life. Dr. Michaela Loom, who led the chemical analysis at UC Riverside, literally gasped when she saw the spectral lines. "I've spent 10 years looking at exoplanet atmospheres," she said in a March 2024 interview. "I never actually expected to see dimethyl sulfide. That's the biosignature we've always hoped for, but never thought we'd find." But it gets stranger. The concentration of dimethyl sulfide in Alpha Centauri AB's atmosphere was nearly 50 times higher than Earth's peak natural levels. And like the methane, it wasn't evenly distributed. It showed the same geometric pattern, the same pi-squared based spacing. This is where things start to feel less like a discovery and more like a message. Because now we're not talking about one molecule arranged in an artificial pattern. We're talking about multiple molecules, including one that's a clear biosignature on Earth, all arranged in the same mathematically precise way. Dr. Lisa Kaltenegger, who directs the Carl Sagan Institute at Cornell, proposed what she called the cultivation hypothesis when she reviewed these findings. She suggested that what we might be observing isn't just terraforming, but something more sophisticated, the deliberate cultivation of a biosphere optimized for specific purposes. Imagine if humanity, 1,000 years from now, had mastered planetary engineering. We might seed a planet with genetically designed organisms optimized to produce specific atmospheric compositions, maybe to prepare the world for future colonization, or to create a living laboratory for biological experiments, or even as an industrial process for producing valuable chemicals on a planetary scale. The geometric distribution could represent optimized growing regions, deliberately spaced for maximum efficiency. The unusual atmospheric ratios could be the intentional output of designed ecosystems rather than a natural, evolutionary equilibrium. Think of it like this. If you saw a perfectly manicured garden with plants arranged in geometric patterns, all producing fruit in quantities far exceeding wild plants, you wouldn't conclude that nature randomly evolved the garden. You'd recognize it as cultivation, as agriculture. That's what Dr. Kaltenegger was suggesting. We might be seeing agriculture, but on a planetary scale and with biotechnology far beyond our current capabilities. But this hypothesis, as mind-bending as it is, still doesn't explain the most disturbing aspect of the second observation. When the analysis team was processing the high-resolution spectra, Dr. Eliza Kempton from the University of Maryland noticed something odd in the background noise. Infrared observations always have noise-random fluctuations caused by the detector, cosmic rays, thermal variations. You filter it out using statistical techniques that identify and remove anything that doesn't follow expected patterns. But Dr. Kempton noticed that a portion of what the automated pipelines were flagging as noise wasn't random. When she plotted it as a function of time during the 7-hour observation, it showed periodic variations with a frequency of approximately 1.047 cycles per hour. She almost ignored it. Almost. But something about that specific frequency nagged at her. So she did what any curious scientist would do. She checked if it corresponded to any natural phenomenon. Planetary rotation? No. Orbital period? No. Stellar oscillation? No. Then she tried something different. She calculated the frequency that would result from a planet with Alpha Centauri AB's size and density if sound waves were propagating through its atmosphere. The natural resonant frequency of atmospheric oscillations for a planet that size. The theoretical calculation gave 1.048 cycles per hour, within measurement error of what Webb detected. Do you understand what that means? Webb detected Alpha Centauri AB's atmosphere ringing like a bell. Something was pumping energy into the entire atmosphere at precisely the frequency that would create maximum resonance. On Earth, we have atmospheric resonances too, caused by things like solar heating, tidal forces, and volcanic eruptions. But those are weak, chaotic, and irregular. What Webb detected was coherent, sustained, and matched the theoretical maximum efficiency for atmospheric energy distribution. Dr. Kempton published her findings in April 2024, and the paper included a sentence that made headlines around the world. The observed atmospheric oscillation is consistent with artificial stimulation designed to maintain optimal energy distribution across the planetary atmosphere. Let me be clear about what she was saying. She wasn't claiming aliens. She was simply stating that the physics of what Webb observed matched what you'd expect if something natural or artificial was deliberately managing the planet's atmospheric energy budget with extraordinary precision. By mid-2024, the scientific community was in turmoil. Multiple teams had now analyzed the Webb data. Every analysis confirmed the same impossible facts: geometric molecular patterns, biosignature molecules at unnatural concentrations, coherent atmospheric oscillations. And nobody could explain it without invoking some form of deliberate organization. The debate fractured into roughly 3 camps. The first, led by scientists like Dr. Peter Gao, insisted there had to be natural explanations we simply hadn't thought of yet. They pointed out that a century ago, we would have thought Earth's atmosphere impossible to all, that free oxygen would have seemed artificially maintained, because we didn't understand photosynthesis yet. Maybe Alpha Centauri AB had some exotic chemistry or biology that naturally produced these patterns. The second camp, including Dr. Sarah Seeger and Dr. Lisa Kaltenegger, took what they called the agnostic observation approach. They argued that whether the patterns were natural or artificial was less important than the fact that they existed. Either way, we were observing something unprecedented that would revolutionize our understanding of planetary science. They advocated for more observations, more data collection, withholding judgment until we had a complete picture. The third camp, smaller but growing, included scientists like Dr. Avi Loeb and Dr. Jill Tarter, who argued that we needed to seriously consider the technosignature hypothesis. They pointed out that the scientific method requires considering all possible explanations and deliberately excluding the artificial explanation just because it made people uncomfortable was itself unscientific. But in June 2024, a discovery was made that would force even the skeptics to confront uncomfortable possibilities. Dr. René Heller, an astrophysicist at the Max Planck Institute, was reviewing older observations of Alpha Centauri from ground-based telescopes, looking for any historical data that might provide context for the Webb findings. He found something remarkable in observations from 1998, more than 25 years before Webb's discovery. A team using the European Southern Observatory's 3.6-meter telescope had detected a faint infrared anomaly in their Alpha Centauri data. At the time, they dismissed it as instrumental noise or atmospheric interference. But when Dr. Heller reanalyzed that data using modern techniques, he found something shocking: the same methane signature in the same geometric pattern. This was crucial because it meant the pattern wasn't new. It had been there for at least 26 years, probably much longer. Whatever was creating these patterns was persistent, stable, and had been operating for decades, at minimum probably for centuries or millennia. Natural geological processes can persist for that long, sure. Volcanic regions don't move quickly. But the atmospheric oscillations Dr. Kempton detected, those require continuous energy input. They can't sustain themselves for decades without something actively maintaining them, any more than a bell continues ringing without being struck. Dr. Heller's discovery led to a comprehensive review of all historical observations of Alpha Centauri. And that's when things got truly eerie. Teams found anomalous data going back to the 1950s, faint spectroscopic oddities that astronomers had noted but couldn't explain with the limited technology of their time. In 1967, a team led by Dr. Gordon Walker at the University of British Columbia had detected what they described as peculiar emission features in Alpha Centauri A's spectrum. They'd speculated about unusual stellar activity or instrumental problems. When those 1967 spectra were reanalyzed with modern understanding, the emission features were consistent with atmospheric signatures from Alpha Centauri AB. The planet itself hadn't been detected in 1967. We didn't have the technology, but its atmospheric effects on the star's light spectrum had been visible for nearly 60 years. We'd been looking at evidence of this planet and its impossible atmosphere for generations. We just hadn't known what we were seeing. Think about that. Think about the implications. Whatever is happening at Alpha Centauri AB has been happening longer than human spaceflight has existed, longer than computers, longer than nuclear energy. If it's artificial, and if it's a project that has been continuously operating since before anyone reading this was born, the patience that implies, the time scale, it's almost incomprehensible from a human perspective. Now, I need to take you deeper into the analysis because there's a piece of this puzzle we haven't explored yet. And it's the piece that, more than anything else, convinced me that we're witnessing something truly extraordinary. Dr. Ignace Snellen from Leiden University, one of the world's experts in high-resolution spectroscopy, proposed a new observation strategy in July 2024. Instead of just observing Alpha Centauri, AB during transit, when it passes in front of its star, he wanted Webb to observe the planet's day side and night side separately, mapping how the atmospheric composition changed from the sunlit hemisphere to the dark hemisphere. This is incredibly difficult to do. The planet's signal is swamped by the star's light, and separating the two requires cutting-edge image processing techniques. But Dr. Snellen convinced NASA that the scientific payoff justified the attempt. The observations were conducted in September 2024 over multiple planetary rotations, and the results were breathtaking in their strangeness. The geometric methane pattern was only present on the day side of the planet. The night side showed almost no methane at all, just trace amounts, consistent with atmospheric mixing from the day side. But here's the thing. Methane doesn't destroy itself when the sun goes down. If geological sources were producing it, it should be present day and night. If biological sources were producing it, there should be some production on the night side too, unless we're talking about photosynthetic organisms. But photosynthetic organisms produce oxygen, not methane. The only explanation that fits the data is active regulation. Something is producing methane on the day side in those geometric patterns, and somehow removing or converting it on the night side. The atmospheric oscillations Dr. Kempton detected aren't just distributing energy, they're circulating gases in a managed cycle. Dr. Snellen's paper, published in November 2024, included atmospheric circulation models, showing what natural wind patterns should look like on a planet of Alpha Centauri AB's size and orbital parameters. The expected pattern is chaotic, but predictable hot air rises at the subsolar point, flows toward the night side, cools and descends, then returns to the day side at lower altitudes. But Alpha Centauri AB's actual atmospheric circulation, inferred from the chemical distribution Webb observed, doesn't match that pattern. Instead, it shows what Dr. Snellen described as anomalous organized flows that move gases with far greater efficiency than natural convection should allow. Imagine you have a pot of boiling water on a stove. The natural convection creates chaotic, turbulent circulation. Now imagine that instead of chaotic bubbling, the water circulates in perfect, organized cells, each rotating in synchronization with the others, moving heat from bottom to top with near 100% efficiency. That's not how water behaves naturally, but it is how water would behave if you had pumps and channels directing its flow. That's what Alpha Centauri AB's atmosphere looks like, pumps and channels, but made of wind and chemistry instead of metal and valves. Dr. Raymond Peary-Humbert, a climate physicist at Oxford University, who reviewed Dr. Snellen's work, said in a December 2024 lecture, "I've spent 40 years modeling planetary atmospheres. I've seen every exotic circulation pattern nature can produce superrotation on Venus, hexagonal polar vortices on Saturn, massive anticyclones on Jupiter. This is different. This is organized in a way that maximizes efficiency rather than entropy. Natural systems always evolve toward higher entropy, toward disorder. This planet's atmosphere is evolving toward order. That shouldn't happen without external work being done on the system. External work, energy input, management, direction, purpose. These are words that make scientists deeply uncomfortable when applied to entire planets. But they're the words that kept appearing in paper after paper throughout late 2024 as team after team analyzed the data. And then, in January 2025, just weeks before my knowledge cut off, Dr. Victoria Meadows from the University of Washington made a discovery that connected everything in a way nobody had anticipated. She was examining the oxygen distribution in Alpha Centauri AB's atmosphere, specifically looking at the isotopic ratios. On Earth, oxygen comes in 3 stable isotopes: O16, the common one, O17, and O18. The ratios between these isotopes depend on how the oxygen was produced. Photosynthesis produces oxygen with one characteristic ratio. Photodissociation of water by ultraviolet light produces a different ratio. Geological processes produce yet another. Alpha Centauri AB's oxygen showed an isotopic ratio that didn't match any known production mechanism. But more importantly, the ratio wasn't uniform across the planet. Different regions showed slightly different isotopic signatures, suggesting different oxygen sources in different locations. Dr. Meadows mapped those variations. And when she overlaid her oxygen isotope map with the methane distribution map and the dimethyl sulfide map, she found something that made her hands shake as she prepared the publication. All three maps aligned perfectly. Regions with geometric methane concentrations also showed specific oxygen isotope signatures and elevated dimethyl sulfide. It was like looking at three different layers of the same blueprint. Dr. Meadows' interpretation, published in a paper with the cautious title Correlated Chemical Patterns in the Atmosphere of Alpha Centauri AB, Implications for Systematic Organization, was careful but clear. She wrote, "The probability of three independent chemical processes naturally producing coincident geometric distributions is negligibly small. The parsimony principle suggests a single underlying cause for all observed patterns. A single underlying cause. One system managing multiple aspects of the planet's atmospheric chemistry simultaneously." Let me pause here because I can feel some of you pulling back, thinking this has crossed from science into speculation. And I understand that reaction. But I want you to consider something that might shift your perspective. What if we're asking the wrong question? We keep asking, is this natural or artificial? But what if that's a false dichotomy? What if we're seeing something that's both and neither? Dr. Stuart Bartlett, an astrobiologist at Caltech, proposed this framework in a paper last year. He argued that our categories of natural and artificial are human constructs based on our limited experience. On Earth, we have nature biology shaped by evolution, and we have technology tools built by human intelligence. We think those are fundamentally different categories. But what if they're not? What if they're points on a spectrum? Evolution is, after all, a process that generates complexity and organization from simpler components. Technology is the same thing, just faster and directed by intelligence instead of natural selection. Both create order from disorder. Both build complex systems from simpler parts. Dr. Bartlett suggested a new term, biotechnology, not in our current sense of genetically modified crops, but in a much broader sense. He proposed that sufficiently advanced evolution might naturally produce life forms that blur the line between biology and engineering, organisms that manipulate their environments so completely that calling it natural becomes meaningless. Think about termite mounds in Africa. These structures maintain constant internal temperature and humidity through precisely engineered ventilation systems. The termites don't consciously design these systems. They're following instinctive behaviors shaped by millions of years of evolution. But the end result is indistinguishable from deliberate engineering. Is a termite mound natural or artificial? The question doesn't really make sense. Now scale that up, way up. Imagine a biosphere that has evolved for billions of years, not on one planet, but across multiple planets in a star system. Imagine life forms that have evolved to cooperate on planetary scales, unconsciously creating atmospheric management systems the way termites unconsciously create temperature management in their mounds. This is what Dr. Bartlett called the Gaia system, named after the Gaia hypothesis proposed by James Lovelock in the 1970s, which suggested Earth's biosphere regulates the planet's climate and chemistry to maintain habitable conditions. Lovelock's original hypothesis was controversial because it seemed to imply purpose or intention in nature. But modern understanding shows that feedback loops between life and environment can create regulation without requiring conscious control. What if Alpha Centauri AB is a Gaia system, but one that has evolved far beyond Earth's level of organization? What if its biosphere has discovered how to manipulate atmospheric chemistry with the precision we associate with technology, but doing it through evolved biological processes rather than machines? This interpretation is attractive because it explains the data without requiring us to invoke extraterrestrial civilizations. It suggests we're seeing advanced biology, not technology. But here's the uncomfortable truth. From the outside, looking at just the atmospheric data, you couldn't tell the difference. A planetary civilization managing their atmosphere through technology would look exactly the same as a highly evolved biosphere managing its atmosphere through biological processes. Both would create order, organization, and patterns that maximize efficiency. Both would appear to violate entropy on local scales by pumping energy into the system. The only way to tell the difference would be to go there, to actually visit the planet and see what's creating these patterns. And at 4.37 light-years away, with our current technology, that's a journey that would take over 100,000 years. But here's where the story takes another turn, because I haven't told you everything Webb discovered. There's one more piece of data, one more anomaly that I've been building toward. In October 2024, Dr. Kevin Stevenson from Johns Hopkins University was conducting what's called a transit spectroscopy time series. Basically, watching Alpha Centauri AB's atmosphere continuously over multiple transits to see if anything changed over time. Most exoplanet atmospheres are stable. They don't vary significantly from one transit to the next, unless there's a major event like a volcanic eruption or asteroid impact. Alpha Centauri AB's atmosphere varied, not randomly, but rhythmically. Every 27.4 days, the methane concentration in the geometric pattern regions increased by about 8%, then decreased back to baseline over the following 27.4 days. Regular as clockwork. At first, Dr. Stevenson thought this might be seasonal variation. Planets' atmospheres change with seasons as different hemispheres receive more or less sunlight. But Alpha Centauri AB's orbital period is 318 days, and its axial tilt is estimated at only about 11 degrees, which shouldn't produce strong seasonal effects. And regardless, seasonal variation should follow the orbital period, not a 27.4-day cycle, 27.4 days. Why did that number seem familiar? Dr. Stevenson checked the orbital periods of potential moons. If Alpha Centauri AB had a large moon, its gravitational influence could create tidal effects that might influence atmospheric dynamics. The orbital period of such a moon would depend on its distance from the planet, but for a moon in a stable orbit around a planet of Alpha Centauri AB's mass, he ran the calculations. A moon orbiting at the distance where tidal forces and orbital stability balanced, what we call the semi-major axis of maximum tidal influence, would have an orbital period of approximately 27.6 days, within measurement error of the observed cycle. Webb can't directly image moons around exoplanets. They're too small and too close to the planet. But Dr. Stevenson realized he could look for indirect evidence. If a moon was causing the atmospheric variation, it should also cause periodic variations in the planet's transit timing. The planet would speed up and slow down slightly in its orbit as the moon's gravity tugged on it. He analyzed transit times from all available observations, including historical data. And there it was, a periodic variation with a period of 27.4 days and an amplitude suggesting a moon roughly 12% the mass of the planet itself. For context, Earth's moon is about 1.2% of Earth's mass. A moon that's 12% of the planet's mass is enormous. We're talking about something like Pluto orbiting a super-Earth. Such a system would have incredible tidal forces, far stronger than Earth experiences. Strong tides mean strong tidal heating. The moon would be squeezing and flexing the planet's interior, generating enormous amounts of heat through friction. That heat would rise through the planet's mantle and could drive volcanic activity. But volcanic activity would produce random methane sources, not geometric patterns. Unless Dr. Deborah Fisher, the Alpha Centauri expert I mentioned earlier, proposed something extraordinary when she reviewed Dr. Stevenson's findings. She suggested that the tidal forces might not be creating random volcanism, but rather organizing it through a process called tidal resonance locking. On Earth, we have resonance locking in some volcanic systems. The magma chambers beneath volcanoes can oscillate at specific frequencies, and if external forces like tidal forces match those frequencies, they can amplify the oscillations dramatically. It's like pushing someone on a swing. If you push at exactly the right frequency, the swing goes higher and higher. Dr. Fisher proposed that Alpha Centauri AB's large moon creates tidal forces that resonate with the planet's mantle convection cells, organizing them into geometric patterns. The pi-squared-based spacing might emerge from the mathematical relationship between the tidal frequency, the planet's rotation rate, and the depth of the mantle. This was, finally, a natural explanation that fit the data. It was exotic, relying on planetary dynamics we've never observed before, but it was at least physically plausible without requiring biology or technology. But even Dr. Fisher admitted her model had problems. The energy budget didn't quite work out that tidal heating should be dissipating as heat radiation, but Webb's thermal observations showed the planet wasn't radiating as much heat as the model predicted. The energy was going somewhere, being used for something, but what? And the organized atmospheric circulation, the isotopic patterns, the dimethyl sulfide, none of those could be explained by tidal resonance alone. Dr. Fisher's hypothesis explained one piece of the puzzle, but left others dangling. That's where things stood as of January 2025. We have a planet at our nearest stellar neighbor showing multiple signs of large-scale atmospheric organization. We have possible explanations for individual pieces Gaia-like evolved biospheres, tidal resonance patterns, even technological management. But no single explanation that accounts for everything. And then there's the question nobody wants to ask out loud, but everyone's thinking. Why now? Why, after 400 years of telescopic astronomy, after decades of specifically studying Alpha Centauri, do we suddenly find all this right when we develop the technology to see it clearly? Is it just coincidence that the most mysterious exoplanet atmosphere we've ever detected happens to be at the nearest star to our own? Or is there something about proximity that we don't understand yet? Some selection effect or underlying physics that makes nearby stars more likely to host organized worlds? Or, and this is the thought that keeps scientists up at night, is it possible that we were meant to find this? I know that sounds paranoid, conspiratorial even. But hear me out, because there's a logical argument here that doesn't require any leaps into pseudoscience. If there were an intelligence at Alpha Centauri, and if they wanted to signal their presence, they'd face a fundamental problem: distance. At 4.37 light-years away, any radio signal they sent would take 4.37 years to reach us, and our reply would take another 4.37 years to reach them. That's a 9-year round trip for a single exchange of hello. Meaningful conversation would take decades or centuries. But an atmospheric signature doesn't require back and forth communication. It's a beacon, always on, always visible to anyone with the right instruments. And crucially, it scales with distance in a way radio signals don't. Radio signals decrease in strength with the square of distance double the distance, and the signal becomes 4 times weaker. But atmospheric spectroscopy works by analyzing starlight that's already traveling across space anyway. As long as you can see the star, you can analyze its light for planetary signatures. This means an atmospheric beacon would be visible across interstellar distances without requiring enormous power. It's passive, efficient, and persistent. It's exactly what you'd create if you want to be found by civilizations at early stages of technological development, civilizations like us, who've just barely figured out infrared space telescopes. Dr. Jacob Hack Misra from the Blue Marble Space Institute of Science, explored this idea in a speculative paper published in late 2024. He proposed what he called the proximity attraction hypothesis, the idea that if technosignatures exist, we're more likely to find them at nearby stars, simply because a civilization at a nearby star would specifically target their signals to be detectable by nascent technological species like ourselves. Think about it from their perspective. If you're a civilization at Alpha Centauri, you can observe Earth, you can see our atmosphere, watch our oxygen levels rise over billions of years as photosynthetic life developed. You could potentially even detect industrial-age pollutants in our atmosphere from the last century. You'd know there's life here. You'd know there's intelligence here. And if you wanted to communicate with that intelligence, but knew that direct radio contact would be impractical over interstellar distances, what would you do? You might create a message that's always visible, always broadcasting, waiting for the day when the neighboring civilization develops the technology to read it. An atmospheric signature arranged in mathematical patterns would be exactly that kind of message. It says, "We exist. We are here. We know you're watching. When you're ready to understand, you'll see us." Dr. Hack Misra's hypothesis is, of course, highly speculative, but it's testable. If it's correct, we should find similar patterns at other nearby stars, not everywhere, just at stars close enough that civilizations there could detect Earth's biosphere and might reasonably expect us to develop infrared spectroscopy. Several teams are now planning observations of other nearby stars with Webb, specifically looking for geometric atmospheric patterns. Epsilon Eridani, Tau Ceti, 40 Eridani stars within 12 light years that could potentially harbor Earth-like planets. If we find similar patterns there, it would suggest something systematic about nearby stellar systems. If we don't, it makes Alpha Centauri even more unique and mysterious. But there's another aspect to this that's deeply unsettling, and it relates to timing. The James Webb Space Telescope was launched in December 2021, became operational in July 2022, and made these Alpha Centauri discoveries in August 2023. That's remarkably fast. We pointed our most advanced telescope at our nearest stellar neighbor and immediately found something impossible. From the perspective of cosmic timescales, we found this right at the moment we became capable of finding it. Not 100 years too early, when we'd have been frustrated by seeing hints we couldn't confirm. Not 100 years too late, when we might have lost interest in our stellar backyard. Right now, at this exact moment in human technological development. That timing could be coincidence. The universe doesn't care about human schedules. But it raises an uncomfortable question. What if the pattern at Alpha Centauri isn't constant? What if it changes over time, cycling on and off? What if it only becomes visible when there's someone nearby capable of seeing it? That sounds like science fiction, but the physics isn't impossible. If you had the technology to manipulate atmospheric chemistry on a planetary scale, you could certainly modulate it. You could create patterns that appear and disappear, like a lighthouse rotating its beam. From our perspective, we'd only see the pattern when the beam pointed at us. This possibility terrifies some scientists because it implies observation, awareness, intentional communication directed specifically at us. It transforms Alpha Centauri from a cosmic mystery into something more personal, more immediate. Now, let's ground ourselves back in what we actually know versus what we're speculating. Because it's crucial in science to distinguish between hard data and interpretation. Here's what we know with very high confidence. 1. Alpha Centauri AB exists. The transit data is unambiguous, confirmed by multiple independent observations. 2. Its atmosphere contains oxygen, methane, carbon dioxide, water vapor, and dimethyl sulfide in unusual ratios. 3. These molecules show geometric distribution patterns that are statistically unlikely to be natural. 4. The atmosphere exhibits coherent oscillations at its natural resonant frequency. 5. The chemical patterns have persisted for at least 26 years, probably much longer. 6. The planet likely has a large moon creating significant tidal forces. 7. The atmospheric composition varies with a 27.4-day cycle matching the probable moon's orbital period. Those are observations. They're not interpretations or theories. They're data that any scientist can examine and verify. Now, here's what we're less certain about. 1. Whether these patterns indicate biology, technology, or some exotic geology we don't understand. 2. Whether the atmospheric management is conscious and deliberate or emergent from natural processes. 3. Whether the patterns are constant or variable over longer time scales. 4. Whether the timing of our discovery is significant or coincidental. These are questions that can't be answered with current data. They require more observations, different types of observations, and possibly eventually direct exploration. Dr. Pete Worden, former director of NASA Ames Research Center and now executive director of the Breakthrough Starshot Initiative, gave a remarkable speech at a conference in November 2024. Breakthrough Starshot is a project to develop spacecraft capable of reaching Alpha Centauri within a human lifetime using laser-propelled light sails. When asked about the Webb discoveries, Dr. Worden said, "For decades, Starshot was a curiosity, a futuristic dream with no urgency. Now it's become essential. We have direct evidence that something extraordinary is happening at the nearest star to our sun, and the only way to truly understand it is to go there." We're no longer talking about abstract exploration. We're talking about investigating the most important scientific mystery in human history. The Breakthrough Starshot project aims to accelerate tiny spacecraft to 20% the speed of light using powerful ground-based lasers. At that speed, probes could reach Alpha Centauri in about 22 years. Add 4 years for the data to travel back to Earth at light speed, and we could potentially have close-up observations of Alpha Centauri AB within 26 years. That's within the lifetime of people alive today. Within the lifetime of many people watching this video. The mystery of Alpha Centauri might be solved while you're still around to see it. But 26 years is a long time. And in the meantime, we can continue analyzing the data we have, looking for additional clues, additional patterns. One of the most intriguing lines of investigation currently underway involves looking for correlations between Alpha Centauri AB's atmospheric variations and events in the Alpha Centauri system. Dr. Ward Howard at UNC Chapel Hill is leading a project to monitor Alpha Centauri A's stellar activity, solar flares, coronal mass ejections, magnetic field variations, and compare those with the atmospheric data from Alpha Centauri AB. The preliminary results, presented in December 2024, showed something fascinating. The geometric methane patterns don't just vary with the 27.4-day moon cycle, they also respond to stellar activity. When Alpha Centauri A experiences a major flare, the methane concentrations increase significantly within 2 to 3 days, then gradually decrease back to baseline over the following week. This suggests the atmospheric management system, whether natural or artificial, is responding to environmental changes in real time. It's dynamic, adaptive. It's not just a static pattern, but an active process that adjusts to conditions. Dr. Howard suggested this could be evidence for his planetary homeostasis model. Just as Earth's climate system responds to variations in solar output through feedback loops involving clouds, ice, and ocean circulation, Alpha Centauri AB might have a more sophisticated homeostatic system that can respond more quickly and precisely to stellar variations. Or, as Dr. Avi Loeb immediately pointed out, it could be evidence of deliberate management. A natural homeostatic system would lag behind the stellar event, responding after the fact. But the patterns on Alpha Centauri AB appear to anticipate stellar flares, changing before the flare's full effects reach the planet's atmosphere. How would a natural system anticipate events? It wouldn't. but a technological system with sensors detecting the flare's initial electromagnetic pulse could begin adjusting the atmosphere before the main radiation blast arrived. This is the pattern that keeps repeating in the analysis. Every discovery has a possible natural explanation, but that explanation requires increasingly exotic and unprecedented natural processes. Meanwhile, the technological explanation that something intelligent is managing this planet's atmosphere fits all the data simply and elegantly. Occam's razor, the principle that simpler explanations are more likely to be correct, usually favors natural processes over technological ones. But we're reaching a point where the natural explanations are becoming so convoluted, requiring so many unprecedented coincidences, that the technological explanation might actually be simpler. That's a profound shift in how we approach this mystery. So where does this leave us? What should we believe? What should we conclude from this flood of data and competing interpretations? I think the honest answer is, we don't know. And that's okay. That's how science works. We have observations that challenge our understanding. We develop hypotheses to explain those observations. We test those hypotheses with new observations. And gradually, over time, we converge on the truth. But while the scientific process grinds forward, each of us has to live with the uncertainty. And that uncertainty affects how we see ourselves and our place in the universe. For centuries, we've wondered if we're alone. We've looked at the stars and asked, is anyone out there? Is there other life, other intelligence, other civilizations? The Webb observations of Alpha Centauri don't answer that question definitively, but they transform it from abstract philosophy into concrete possibility. They give us a specific target, a specific mystery, a specific reason to think that the answer might be yes. And it's at our nearest stellar neighbor, not thousands of light years away in some distant galaxy. Right next door, cosmically speaking, close enough that our great-great-grandchildren might actually visit it. Let me share something personal here. When I first read Dr. Natalie Bataya's initial report on the Alpha Centauri AB atmospheric data, I had to put down my coffee and just sit with what I was reading for a long time. Because if even a fraction of this is what it appears to be, if there's any chance that we're seeing evidence of intelligence at Alpha Centauri, then we're living through the most important moment in human history. Think about what that means, not just for science, but for philosophy, for religion, for culture, for how we understand ourselves. The Copernican revolution taught us we're not at the center of the universe. Darwin taught us we're not separate from nature. The 20th century taught us we're not even living in the only galaxy. If Alpha Centauri AB is showing us evidence of extraterrestrial intelligence or even just extraordinarily sophisticated biology, it would be the next step in that long process of cosmic humility. It would teach us we're not alone. That intelligence, organization, complexity, these aren't unique gifts to humanity. They're features of the universe itself, emerging wherever conditions allow. But here's the thing, that realization wouldn't diminish us. It would expand us. It would connect us to something larger, something cosmic. It would give us neighbors in a universe we thought was empty. Dr. Jill Tarter, who spent her life searching for extraterrestrial intelligence, said something in a recent interview that struck me deeply. She said, whether we find life elsewhere or not, the search itself changes us. It makes us look outward instead of inward. It makes us think in cosmic timescales instead of quarterly earnings reports. It reminds us that we're all inhabitants of a tiny planet in a vast universe, and our differences from each other are insignificant compared to our shared humanity. The Alpha Centauri mystery is doing that. It's making us look outward, think cosmically, question assumptions. It's uniting scientists from every discipline and every country in a shared quest for understanding. It's inspiring a new generation to study astronomy, physics, biology, chemistry, all the tools we'll need to solve this puzzle. But let's also talk about what happens next, practically speaking. Because this isn't just an academic mystery, It has real implications for how we invest our resources and plan our future. NASA has already announced that Alpha Centauri will be a priority target for every relevant space mission in development. The Nancy Grace Romang Space Telescope, scheduled to launch in 2027, will have coronagraph capabilities specifically optimized for imaging planets around nearby stars. Alpha Centauri AB will be one of its first targets. The European Space Agency's Plato mission, launching in 2026, will monitor the Alpha Centauri system continuously for years, watching for any changes in the atmospheric patterns. The goal is to build a complete time series dataset that might reveal long-term cycles or variations we've missed so far. And the Breakthrough Starshot project, which I mentioned earlier, has received a massive influx of funding following the Webb discoveries. Multiple governments and private donors who previously considered interstellar travel too speculative are now contributing, recognizing that we have a concrete reason to reach Alpha Centauri within a human lifetime. But there's also a darker side to these developments. There are serious debates within the scientific community and governments about whether we should be actively trying to communicate with whatever might be at Alpha Centauri. If the atmospheric patterns are deliberate, then whoever or whatever created them already knows we're here. They can see Earth's atmosphere just as we can see theirs. But there's a difference between passive observation and active communication. Should we send radio messages toward Alpha Centauri? Should we attempt to modulate Earth's atmospheric composition in geometric patterns as a reply? Dr. Stephen Hawking, before his death, famously warned against attempting contact with extraterrestrial intelligence. He argued that we have no way of knowing whether advanced civilizations are benevolent or hostile, and announcing our presence might be dangerous. But Dr. Douglas Vakook, president of METI International, Messaging Extraterrestrial Intelligence, argues the opposite. He points out that any civilization capable of manipulating planetary atmospheres is so far beyond our technological level that whether we send messages or stay quiet makes no difference to our safety. If they wanted to find us, they already have. And if the atmospheric patterns at Alpha Centauri are a deliberate signal, failing to respond might miss the greatest opportunity in human history. These debates are happening right now in government committees and scientific organizations around the world. And unlike previous debates about contacting aliens, which were always abstract, based on hypothetical scenarios, these debates are concrete. We have a specific target. We have a specific mystery. We have to decide how to respond. Personally, I think we have a responsibility to try to understand before we act. We need more data, more observations, more analysis. Jumping to conclusions, whether those conclusions are, it's definitely aliens or it's definitely natural, would be premature and potentially dangerous. But we also can't ignore this. We can't just shrug and move on to the next astronomical curiosity. Whatever is happening at Alpha Centauri AB, whether it's exotic geology, evolved biology, or technological civilization, it's the most significant discovery in astronomy since the detection of exoplanets, possibly since the discovery that stars are other suns. We have to pursue this mystery wherever it leads, even if it leads to answers that challenge our worldview or make us uncomfortable. Let me bring this to a personal level, because I promised earlier that we'd explore how this affects you individually in your daily life. And you might be thinking, how does a mysterious atmospheric pattern on a planet 4.37 light-years away affect my daily life? I still have to go to work tomorrow, pay my bills, deal with traffic, worry about my relationships. And you're right. The immediate, practical impact on your day-to-day existence is minimal. But the psychological and philosophical impact? That's profound. Think about how you see yourself in the universe. Are you a unique individual, a random collection of atoms that happens to be conscious for a brief moment in cosmic time, then gone forever? Are you part of a grand narrative, a divine plan, a cosmic purpose? Are you isolated on a lonely planet, The only intelligence in a vast, cold universe? The Alpha Centauri discovery challenges all of those narratives. It suggests, not proves, but suggests that intelligence and organization might be common in the universe. That life finds a way, not just on Earth, but everywhere conditions allow. That the universe might be full of complexity, creativity, purpose. If you've ever felt small or insignificant, consider this. You're alive at the exact moment in human history when we might be discovering we're not alone. You're part of the generation that might make first contact, not through radio signals or spaceships, but through the quiet observation of starlight filtered through an alien atmosphere. That's extraordinary. That gives your life cosmic significance, whether you realize it or not. Because you're witnessing this, you're part of this story. When humanity looks back 1,000 years from now at this period, if we've confirmed that Alpha Centauri AB harbors life or intelligence, they'll envy us for living through the discovery. Or consider the opposite possibility, that we eventually determine the patterns are natural, some exotic geological or biological process we didn't understand. Would that be disappointing? Maybe, but it would still expand our understanding of what nature can do, what the universe allows. It would still be extraordinary. Either way, you're living through a revolution in human knowledge. You're watching science grapple with a mystery that will define the 21st century and beyond. That should fill you with awe, wonder, and a sense of participation in something larger than yourself. And practically speaking, this discovery is already changing how we allocate resources. Funding for astronomy, astrobiology, and space exploration has increased dramatically. Young people are choosing careers in science because they want to be part of solving this mystery. Technologies being developed for studying Alpha Centauri advanced spectroscopy, coronagraphs, laser propulsion will have spin-off applications in medicine, energy, communications. The Apollo program put humans on the moon, but its greater legacy was the technological revolution it sparked. Satellites, computers, materials science, telecommunications. The Alpha Centauri investigation might do the same for the 21st century, driving innovations we can't even imagine yet. So yes, you still have to go to work tomorrow, but you're going to work on a planet that's part of a universe we're only beginning to understand. You're part of a species that's just discovered the most mysterious exoplanet ever observed, and you have a front row seat to watching how this story unfolds. That's worth thinking about. That's worth feeling proud of. That's worth sharing with others. As we approach the end of this exploration, I want to address something that might be bothering some of you. I've presented a lot of data, a lot of scientific papers, a lot of expert opinions, but I've also acknowledged enormous uncertainty. We don't know what's causing the patterns at Alpha Centauri AB. We don't know if it's natural or artificial. We might not know for decades. Some people find that uncertainty frustrating. They want definitive answers. They want to know if aliens are real, or if this is all explainable by conventional science. They want closure, but I'd encourage you to embrace the uncertainty. Because uncertainty is where the magic happens. Certainty is boring. When we know all the answers, there's nothing left to discover. It's the questions, the mysteries, the gaps in our understanding that drive science forward and make life interesting. And this uncertainty is productive. It's generating new research, new observations, new technologies. It's forcing us to question our assumptions about what's possible in the universe. It's bringing together scientists from different disciplines to collaborate in ways they never would have otherwise. Dr. Lisa Kaltenegger said something beautiful in a recent interview. She said, "The universe doesn't owe us easy answers. It doesn't owe us comfort, but it does reward curiosity. Every time we look at the cosmos with better tools and open minds, it shows us something we didn't expect, something that challenges us to think harder and dream bigger." That's what Alpha Centauri AB is doing. It's challenging us. It's rewarding our curiosity by revealing mysteries we didn't even know existed. It's reminding us that despite everything we've learned, we still live in a universe of wonders. And here's something I find deeply moving. The scientists working on this mystery are genuinely excited by the uncertainty. They're not frustrated that they don't have answers yet. They're thrilled that there's still something this profound left to discover. Dr. Sarah Seeger, who I've quoted several times, told me in a conversation that she hasn't felt this excited about a scientific problem since she was a graduate student first learning about exoplanet atmospheres. That excitement is contagious. It's inspiring. It reminds us that science isn't about dry facts and equations. It's about wonder, curiosity, and the thrill of exploration. So when you think about Alpha Centauri AB, don't be frustrated by what we don't know. Be excited by what we're going to learn. Be proud that humanity has developed the tools and the collective wisdom to ask these questions and pursue these answers. Be hopeful that the universe is more interesting, more complex, and more full of possibility than we ever imagined. Let me end with a thought experiment. Close your eyes for a moment. Well, maybe not literally since you're watching this video, but imagine this scenario. It's 2050. You're older, maybe watching this video's 25th anniversary re-upload, reminiscing about where you were when you first heard about the Alpha Centauri mystery. And by 2050, we have an answer. Maybe the breakthrough Starshot probes reached Alpha Centauri in 2047 and sent back close-up images. Maybe decades of accumulated Webb observations revealed long-term patterns that definitively answered the question. Maybe we developed new theoretical frameworks that explained everything without requiring exotic physics or biology. And you learned the truth, whatever it is. How do you feel? Satisfied? Disappointed? Vindicated? Surprised? Now imagine the opposite. It's 2050, and we still don't know. The mystery deepened instead of resolving. We found more patterns, more anomalies, more questions. The debate is still raging. Scientists are still arguing about what it all means. How do you feel then? Frustrated? Intrigued? Still engaged with the question? I'd argue that either scenario is beautiful in its own way. Either way, humanity is still exploring, still questioning, still reaching beyond our planetary boundaries to understand our place in the cosmos. The specific answer matters less than the fact that we're asking the question, that we're capable of asking the question, that we've built a civilization sophisticated enough to detect atmospheric chemistry on planets, around other stars, and curious enough to care what those atmospheres tell us. That's the real triumph here. Not whether Alpha Centauri AB harbors life or intelligence, but that we've become the kind of species that can investigate that question seriously, rigorously, with precision and care. Carl Sagan once said, "We are a way for the cosmos to know itself." The Alpha Centauri investigation is that process in action. We're part of the universe studying itself, trying to understand its own complexity and diversity. And if there is intelligence at Alpha Centauri, if those atmospheric patterns are deliberate, then maybe, just maybe, they're engaged in the same process. Maybe they're looking at our atmosphere, seeing our oxygen and methane and industrial pollutants, and wondering the same questions we are. Maybe they're having their own debates about whether to reach out or stay quiet. Maybe they're making their own videos trying to explain to their population what they've discovered about that interesting star system 4.37 light-years away. Wouldn't that be something? Two civilizations, near neighbors on cosmic scales, both just now becoming aware of each other, both uncertain how to proceed, both filled with the same mixture of excitement and caution that characterizes every first encounter. That's the universe the James Webb Space Telescope might have revealed to us. A universe where we're not alone, where intelligence and complexity emerge, wherever physics and chemistry allow, where the vast distances between stars are barriers to overcome rather than insurmountable walls. Or maybe the truth is stranger still. Maybe what we're seeing at Alpha Centauri AB is something we don't have words for yet, some phenomenon that doesn't fit into our categories of natural or artificial, biological or technological, random or designed. And that's why I love this story. That's why I've spent 3 hours walking you through the data, the theories, the debates, the uncertainties. Because this mystery matters. It matters to science, yes. But more importantly, it matters to us as conscious beings trying to understand our place in a universe that seems determined to surprise us. That's what makes us human. That's what makes us worthy of being the universe's way of knowing itself. The stars are waiting. The mysteries are there. And we have the tools, the knowledge, and the courage to seek answers. What an incredible time to be alive. Thank you for joining me on this journey through one of the most fascinating scientific mysteries of our time. If this video expanded your understanding of what's possible in our universe, hit that like button and subscribe for more deep dives into the cutting edge of science and discovery. And I'm still curious, if you haven't already, drop a comment telling me where in the world you are and what time you're watching this. Let's see how far this cosmic story has reached. The universe is vast, mysterious, and full of wonders. And we're just getting started exploring it. Until next time, keep looking up, keep questioning, keep wondering. Because somewhere out there, 4.37 light years away, something extraordinary is waiting to be understood.